Hello, class. So on this video, we'll continue on chapter 4. As a reminder, we're covering all of the 4 sections in this lesson. So we saw in the previous videos that a lot of the things, or basically everything that we talked about in section 3.2/4.1 generalizes to higher order ODEs. Right? So in those sections, we talked about it regarding second order linear ODEs, right? So specifically for linear. And then we see that it generalizes to any order, so nth order linear ODEs, meaning that what matters, what is important, is not the order of the differential equation, but the linearity, right? If it's linear or not. So we saw examples of theorems, right? So the existence and uniqueness for an initial value problem. We went over an example of that and how it generalizes to any nth order linear initial value problem. We also talked about how given an nth order linear ODE, there's always a fundamental set of solutions, right, on some interval, meaning that there are always n linearly independent solutions, right? Meaning that we can always find n functions who are linearly independent on some interval I, and then out of those linearly independent functions, we get the complementary solution, meaning the solution to a linear nth order ODE where everything that's not being multiplied by a derivative of y equals 0, right? So a homogeneous ODE. Lastly, using theorem 2, if we have a non-homogeneous ODE, we can always find the general solution. What do we do? As long as it's linear, right, of course. What do? We find the complementary solution, and then we add to that complementary solution a particular solution, right? What was a particular solution? It was just a solution to the original differential equation, right? So the same method that we used in the case for the second order ODEs, it generalizes same process to nth order linear ODEs. So we saw a couple of examples, right? Specifically, I want to mention that we saw one example in which we're looking at a homogeneous linear, so assuming homogeneous in this class means we're assuming it's linear, right? So we're looking at homogeneous nth order where n is greater than 2 ODEs. And we saw that to find the general solution, it's very easy, right? You just find, so if all the roots are distinct, it's easy, right? If you have repeated roots, then you basically just write down the first solution, right, with one of the roots, right, e to the whatever root you have times x. And then to get other solutions, you just multiply that first solution by x as many times as needed. Right? And in particular, if you have a root of multiplicity, in this example was a root of multiplicity 3, we wanted to have 3 solutions to come out of this root, right? So we got one, just as I mentioned, e to the r times x. In this case, r was 0. And then you just multiply by x to get another one. That's 2 of them. Multiply by x again to get another one, and that's 3 of them. Right? So you want as many solutions as the multiplicity of the root. Right? So we went over this in the previous video. Now let's do an example of a non-homogeneous case. Right? So we still have a linear ODE, right? Third order, constant coefficients. However, in this case, we're looking at something that's non-homogeneous. Since it's a combination of exponentials and cosine, right, in particular e to the x times cosine x, we can use the method of undetermined coefficients. And if you remember for that method, first, always by theorem 3, you find the complementary solution, right? So find a solution when this is equal to 0, right? This would be your g of x. And after that, you want to find a particular solution. And again, since it's a combination of exponentials and cosines, what we can do is just use the method of undetermined coefficients when we choose a form of a particular solution that includes all possible derivatives, all terms that we get from all possible derivatives of g of x. Right, so let's go through the work. So again, first we find a solution to the homogeneous case, right, which is the complementary solution. Right, so we write down the characteristic polynomial. Right, so the power of r corresponds to the power or the order of the derivative. Right, so this is our characteristic polynomial. Then we set it equal to 0. Okay, so then what do we get? We can factor out an r squared, actually. Okay, and then we get solutions. So we get from the root r equals -1, right? We get e to the negative x, right? Negative 1 times x. Now we have a root r equals 0 multiplicity 2. Right? So we need to get two solutions out of this. Right? The first one is always e to the root. Right? In this case, the root is r equals 0. Right? So e to the 0, which is 1. Right? But again, this root has multiplicity 2. We want two solutions to come out of this root. Right? So what do? You just multiply the first solution by x. And now we have two solutions from a root of multiplicity 2, right? So we're done, right? We have three solutions for a third order linear ODE. So the complementary solution is just a linear combination of these. So C1 is the negative x plus C2 times 1 is just C2 plus C3 times x. And remember that this is for all real numbers. Right? So it's already given that these are linearly independent. You don't have to check. Okay, so that takes care of the homogeneous case, right? That's a complementary solution. Now we need to find a particular solution, right? And as I mentioned, we're going to use the method of undetermined coefficients. We could use variation of parameters. There's a way to generalize that as well, but to when we have a linear ODE that's higher order than just order 2. But for now, since we can use the method of undetermined coefficients, let's just use it. So let me rewrite the ODE here so we have it right in front of us. So the method to find the particular solution is exactly the same. So you're looking for a particular solution, y sub p, whose terms, right? So this y sub p is going to have a bunch of terms. You're going to make sure that each term that appears in derivatives of g of x appears in y sub p. And so we've done this particular one before. Right? So I'm not going to spend too much time. You can just go ahead and verify that if you take derivatives of g of x, all terms that you get either look like some constant, right? So let me say some constant a times e to the x cosine x, or, all right, so that's one term that you get, one form of the term. Then you also get something that looks like b, some constant, e to the x sine x. Right? And those are the only terms or forms of terms that you get. And let me do something here because this looks like I'm dividing by g of x, which I'm not doing. So this is our g of x. So again, you can take derivatives again as an exercise. You can verify that all terms that you get either have the form a constant times e to the x times cosine x, or a constant times e to the x sine x. So since those are the only forms of terms that we get from derivatives, right, and this is all possible derivatives, then our particular solution is going to have the form. So some coefficient times e to the x cosine x plus some coefficient times e to the x sine x, right? Where the coefficients are undetermined as of now, right? That's why it's called the method of undetermined coefficients. Right? And then how do you determine these coefficients? You plug this into the ODE. Okay. So you can do that as an exercise. I'm not going to do it because we've done it before, right? But what you would do now is plug into the ODE and equate terms. Right, so this is what we do. Right? And the goal is to determine what A and B are. So really, the only thing that changes in terms of the method of undetermined coefficients is just how to find the complementary solution. In terms of how to do the method of undetermined coefficients, right? When you have a function g of x not equal to 0, as long as it's a combination of exponentials, cosines, sines, and polynomials, it's exactly the same process as before. In terms of how to find a particular solution, just take derivatives of g of x, as many as you need, until you determine, okay, these are all the possible forms of terms that I get, so I want to make sure I include them in my particular solution, in the form of the particular solution. Then you plug that into the ODE, equate both sides of the equation, so whatever's on the left should be equal to whatever's on the right. So equate terms and determine the undetermined coefficient. So again, the only new thing really is how to find the complementary solution. which we saw in the previous example, right? In example 2, we saw that in detail. Okay. So that's method of undetermined coefficients. Now, let's talk about variation of parameters. Now, remember that for variation of parameters, we introduced this method for whenever our g of x, right? So whenever we had a linear ODE where g of x was not equal to was not equal to 0, was not a combination of sine, cosine, polynomials, and exponentials. And again, if it's not one of those, the method of undetermined coefficients doesn't work, because remember, the idea is that you want to find all terms that come from as infinitely many derivatives of g of x. So if your functions don't go to 0, like polynomials, or repeat, like cosine and sine, or just the derivative is itself, like with the exponentials, right? If none of those things happen, then you're going to get infinitely many terms in the derivatives, infinitely many new terms appearing. You can't include, you could write a particular solution like that, but there's no way to solve a system of linear equations with infinitely many coefficients like that. We can't do that. So that's why in chapter 3, we introduced this method of variation of parameters. And the idea was that this works irrelevant or independent of what g of x is, right? We just had a couple assumptions on the differential equation. So first, you have an nth order linear ODE. Right? So again, I'm dividing by the leading coefficient, right? Whatever function was in front of the highest order derivative, in this case, the nth order derivative of y, I divide by that and I get this equation. So what were the assumptions that we needed for the method of variation of parameters? Well, we needed each of the coefficient functions, right, after we've divided by whatever is multiplying the highest order derivative. So each of these, including g of x, whatever's on the other side, all of those have to be continuous on some interval I. Moreover, we either have to be able to find the complementary solution, or we have to have the complementary solution given to us. In the case that the coefficient functions are constants, right, we can find the complementary solution. But the method of variation of parameters was nice in the sense that the coefficients didn't have to be only constants. They can be expressions involving x as well. Right? And the method of variation of parameters worked in that case as well. Again, the only restrictions that we had was that these coefficient functions had to be continuous on some interval I. Okay. So you have that, and then you're either given or you can find the complementary solution on a common interval I. Right? So I here is a common interval in which the coefficient functions are continuous and in which we have the complementary solution, or we can find the complementary solution. In this case, we assume that we already have it. We either found it or it was given to us. So basically, the idea is the same thing that we did for the second order case, is that we're going to assume that our particular solution has this specific form where it's a sum of the n linearly independent solutions that we found for the complementary solution, right? So the y sub i's come from here, from the complementary solution. Okay. And what we do is, right, we can't have them be constants, right? So we multiply them by these functions, u sub 1, u sub 2, up to u sub n. These functions can't be constant, because if they were, this would be part of the complementary solution. So this solution would immediately go to 0 when you plug it into the ODE, right? So instead of that, we assume that the coefficients are functions of x themselves, right? Expressions involving x. And that was the method of variation of parameters, right? And other than that assumption, right, what we did was basically just plug everything into the ODE and solve, right? See what we can simplify. Now, again, just like I did in the second order case, I'm not going to do through all the work, but if you plug in all of the this particular solution and you simplify nicely, you end up with some expression. And then what you do is that to simplify that expression, you make all of these, well, not this, all of these assumptions. Right? So you're going to get a bunch of terms, right? And then you want to simplify, so you make all of those terms basically say, okay, I'm going to assume that my solution has a form in which all of these terms are equal to 0. Right? Remember, that's what we did in the second order case. Right? That simplified the ODE, right? Meaning that in the end, we got this out of it after we set all of these things equal to 0. Right? So then how do we find a solution? Well, we have to find, we need to find U1, U2, U3 up to UN that satisfy these assumptions, right? All of these equations are 0, and that satisfy this equation. Right? And if you remember, what we ended up here was with a system of linear equations where the unknowns are the derivatives of the u's. Right? Those are the unknowns in each of the equations, right? And the y's we know, right? Because the y's come from complementary solution, right? And if we know the y's, we can take the derivatives. So really, all that we need to do is find the u sub i's prime, right? The derivatives, right? So as we did in the previous section, or in the previous time we talked about this, we're going to use Cramer's rule. Right? So you don't have to worry about how that rule works. Right? But the idea is you get these equations for u sub prime, for u prime, sorry. You can determine these equations. What do those end up being? Well, they end up being these Wronskians. Right? If you remember, it was a ratio of Wronskians that we ended up with. So in this notation that I'm using here, right, so we have n functions, right, u sub n, u sub I that we need to determine. So what are the things here? So w is just the Wronskian of the y sub I, so y1, y2, up to y sub n. And I'm going to do an example, okay? But I just want to make sure that all the variables here are determined, so we know what they are. And then what's w sub k? Well, this is almost the same Wronskian, but what you do is you replace the kth column. Right? So instead of working with the kth complementary solution, right, linearly independent complementary solution, what you do is you replace it with a new column. Right? What is that column in the Wronskian? Well, it's going to be a column of all zeros. So I'm going to write it like this. It's going to be a column of all zeros. And then at the end, we're going to have g of x. And then everything else is the same. So then u prime of k is this ratio. And then we solve or find for u prime of k by integrating. And even though we get infinitely many solutions, right? Because this is an indefinite integral, right? So you get infinitely many solutions. We're only interested in one, so we usually take the solution where the arbitrary constant of integration that we get is equal to 0. Right? But this is the idea. Right? And again, I don't spend a lot of time in the derivation because it's basically the same thing as before. You just plug everything, this y sub p in. You make these assumptions that all of these expressions are equal to 0, so that everything simplifies to this last line. Right, that I boxed in orange. Right, so what's most important for us is this equation. This is this equation that we have for each u prime of k, and these definitions. Right? The w is just the usual Wronskian of the y sub i's, and then w sub k is the Wronskian again of the y sub i's, but you remove the column for y sub k and replace it with a column with all zeros and g of x at the end. Right? Okay. So now we're going to see an example. Now, the problem here, which maybe you've already seen, is we're working with higher order derivatives. Right? So differential equations, meaning that we're going to work with differential equations of order 3 or more, because we already know how to do the case where our differential equations order 2. So our determinant now is not going to be a 2 by 2 determinant. It's going to be a 3 by 3 or 4 by 4, etc. And we haven't gone through how to do that. How do you find those determinants? Well, what we're going to do is I'm going to show you how to do it in mathematics, right? Because there's no point in doing it by hand. It's something you can do by computer. You can, if you really want to know how to do it by hand, you can Google it, and there's a formula, right, that you can do by hand. There are shortcuts that simplify the work, but for us, we're just going to use mathematics. Okay, so we're going to do that in the next video.